Hello. Hello. Very good afternoon, everyone. Uh, in the recent years, I have been looking or studying how monsoons and deserts co-evolve. And so today, I thought of giving an overview of these two climate regimes. So just a moment. I'll get this thing working. Okay. So here is climatological surface temperature, a map of climatological surface temperature, monthly mean. So as this thing evolves, you will see that, so before we get into that, most of South Asia, especially land, India, is at the same latitude as Sahara or Middle East. So these are the climatological deserts, arid regions, some of the biggest, largest arid regions on the planet. And we have the strongest monsoon at the same latitude. So there is a very strong zonal asymmetry that occurs in this region, the Afro-Asian sector. Particularly in terms of temperature, look at the surface temperatures in the later part of the year, October, November, they are quite similar as any subtropical system at any subtropical latitude would behave. But come April, May, India tends to have higher temperature at the same latitude as Sahara or Middle East does. So in some sense, India land is more arid, more hot than Sahara is. But once monsoon comes, the whole thing, the whole equation changes. So this thing is not working again. Yeah, the general rule for subtropical climate can be taken from this meridional stream function, mass stream function. This is for March, April, May, but this kind of represents the annual mean. We have strong vertical updraft near the equator, deep tropics, and descent at the subtropics on either side of the equator. This is the classical Hadley cell. So the general rule of climate is that the subtropics, usually you will find most of the deserts and arid regions in the subtropical region. But one exception to this rule is the South Asian monsoon. This is monthly climatological precipitation. You can see that during the monsoon months, there is substantial rainfall over South Asia, but at the same latitudes, it is very, very dry. During non-monsoon months, South Asia behaves like any other subtropical region, typical arid desert region, right? So something happens during the monsoon season that makes it so different than the general rule. So in other words, I think it is fair to say that monsoons are an exception to the general rule of subtropical deserts. Okay. So one of the reasons why I'm interested in understanding this zonal asymmetry, particularly this zonal asymmetry, is because this is a very sharp gradient in rainfall. We have a very strong concentration of rainfall in one region and very arid in the other region. So, but why to compare or why to consider these two systems together, right? So most of the studies focus on either monsoon or deserts, but why to take these systems together? So I would like to invoke one very interesting analogy that Richard Feynman had given, the cosmic game. So Richard Feynman gave a very interesting analogy. He said that the job of physicist, so according to him, there are gods who are playing this game of chess. It's representative of the universe, and we are observers who do not know the rules of the universe or rules of this game. So we are trying to infer these rules. We are trying to interpret these rules by observing gods play this game, right? So this is what physicists do. This is also what climate scientists do or aspire to do. Now, for most of the time, we have been trying to isolate or unravel rules of monsoon, rules of deserts in isolation of each other. But in my opinion, the game here is between the gods of monsoon versus gods of deserts. So these are two very different climate regimes. They are playing by the same rules. So whatever rules apply for physical rules, laws of physics apply for monsoon. Also, the same laws of physics should apply for deserts. But the way desert will use those laws is different than for the monsoon. So can we have the same fundamental theory for both regions that can explain the dynamics or dynamics of these two very different contrasting climates? So that is the idea behind this. So moving on. Yeah. I guess the first we need to teach LLMs the rules of the game. So what I will do is give an overview of the existing theories and how they evolved. Most of you have already been introduced to different theories of monsoon. So I will begin with theories of deserts. And we will go towards how the two work together. So the most ancient theory in the world of deserts is the descending branch of Hadley cells, the subtropical high. So earlier we saw this diagram. This is the mass stream function, meridional mass stream function during MAM, which is sort of representative of the annual mean, right? So you have very almost close to symmetrical Hadley cells in the northern and southern hemisphere, right? And subtropical highs on either side, in either hemispheres. But what happens is during the summer season, when the subtropical deserts are at their most intense, when the climate in these arid regions is at its most intense, also when the monsoon is at its most intense, the summer cell is quite weak. The winter Hadley cell, which goes from the northern hemisphere, this cell is going across equator into the southern hemisphere. That is the strongest cell. So in the absence of a strong descent over Sahara, over northern subtropics, how do we explain deserts or how do we explain subsidence in this region? That had been one challenge. So once again, just want to highlight the theme, how this aligns with the theme that has been recurring in this workshop: zonal mean versus regional asymmetries. So this is one of the reasons why zonal mean theories have their limitations. So the next interesting theory in this to explain this subsidence, especially during summer season, comes from Charney, albedo and radiative cooling. So if we take the climatological top of atmosphere net energy fluxes, the top figure is from Ceres satellite observation and RFI at the bottom. Okay, so this is June, July, August climatology. This is just the top of atmosphere net radiative fluxes. Okay, so red here is positive. So in these regions, from the top of atmosphere, there is net radiative influx into the atmosphere. Radiative heating is occurring from top of atmosphere. But in these regions, Sahara, Middle East, it is sort of close to zero or negative in places. So there is a net radiative cooling, right, in these places, and consistent across observations and reanalysis. Now, what is the consequence of this radiative cooling? Here, this arrow is upwards. It means energy is lost to space, right? So as energy is lost to space, the air parcels will cool, and there is subsidence. And you have this subsidence, convergence in the upper troposphere, divergence in the lower troposphere, right? So this is the main hypothesis, working hypothesis behind Charney's 1975 paper. You can see the difference in albedo This is just a Google Earth image, but you can see the difference here, real color image. Barren soil is very reflective. South Asia receives substantial rainfall and is vegetated, and albedo is relatively low, right? So this difference in albedo has been or had been the main culprit, had been thought to be the main culprit behind this F2R differences between Sahara and South Asia. So now this was also considered to be one of the reasons why we have subsidence over Sahara during JJA. But in the main focus of Charney's paper was a albedo feedback that comes from vegetation. So, for example, especially near the boundaries, near Sahel, the West African monsoon and Sahara, the boundary between these two, if for some reason, let's suppose overgrazing, vegetation decreases, that exposes barren soil, which has higher albedo. Higher albedo, more subsidence in that region. More subsidence leads to enhancement of arid climate in that region, which further creates more barren soil. So this is a positive feedback loop, right? So this was the main hypothesis, main proposition of this paper. Subsequently, it was challenged because its main focus was on extremely local parameters, overgrazing or vegetation, human-induced parameters. Other factors were not considered, especially factors coming from SST, variations in SST. There is substantial interannual, multi-decadal variability in SST, which influences the rainfall in this region. And that has a much stronger effect than albedo does. So this is one important reason why this albedo feedback was not was eventually disregarded or discredited. But I want to spend a moment on this, build on top of this idea, build on this proposition by Charney. So later in 1987, Nilin and Head made an exciting proposition that mass convergence in the lower troposphere. If you divide the troposphere into two parts, upper troposphere, lower troposphere, the mass convergence in lower troposphere can be written as the ratio of net energy fluxes into atmosphere from the top and surface and GMS. Right? So now, please remember this is for a convecting region. There is a cloud here. So whenever there is a cloud, it's a convecting region, most likely ITCZ or monsoon. Okay. So you have low-level mass convergence, upper-level mass divergence. The arrow is downwards, so net energy going into the atmosphere. Okay. Now, there are two assumptions here. It's a steady state and two-layer atmosphere. For land regions, over land regions, because land has lower heat capacity, on longer time scales, surface fluxes, net surface fluxes can be neglected. So this leads to a simplification. The mass convergence, net mass convergence in the lower troposphere is a ratio between F2R, radiative fluxes, and GMS. Now this is a very interesting equation, has some interesting interpretations. This is my take on this equation. On the left side, we have dynamics of the lower troposphere. Numerator is radiation, and denominator, in some sense, represents thermodynamics of the atmosphere. So this is one equation that combines three different aspects of the atmosphere, brings it together, and so this is a simple theory that connects the three different pillars of atmospheric sciences. Now, this was a proposition mainly for convecting regions where F2I is positive. What if we extend this to regions of subsidence, something similar to what Charney thought of doing. Uh, Although later on he also focused on the albedo feedback. Suppose we use this equation for these regions where subsidence is occurring. So F2I is negative. GMS, the sign of GMS needs to be determined. But in general, uh, in a column mean sense, we have subsidence in the lower troposphere, subsidence and divergence in the lower troposphere, and F2I is negative. So negative of divergence, that will be taking into consideration GMS, sign of GMS, we should get a positive term, a positive number, F2R by GMS. So can we extend this to deserts as well? So that's a simple theory, a simple hypothesis. Whether it works or not, we will see. But something that builds on the propositions made by Charney. So in this case, what is GMS? We have seen GMS again and again, and earlier Spencer said that GMS can be thought of as the efficiency with which atmosphere imports MSE in convecting regions. But in deserts, it probably represents, exporting energy in convecting regions. In deserts, it represents the efficiency with which atmosphere imports energy. So we can think of it in this way. This is just a small digression. I thought it's relevant because we were discussing Charney's hypothesis, so I thought of putting it out here at this stage. But the main reason why this did not progress during Charney's time was that he did not consider the horizontal advection terms, which are very important, which have been shown to be very important, especially near surface, surface in deserts. We can get away with ignoring the horizontal advection terms in convecting regions. We can take the WTG approximation. We can also assume that moisture gradients are not so strong, and we can get away with it in convecting regions. But does that assumption hold in regions of descent? That is the question, and it turns out it does not. So we need to consider horizontal advection terms, which is missing in Charney's considerations. And it is for that reason it did not progress further. So if we modify GMS to account for these horizontal advection terms, then we may be able to get an equation of this sort working for the deserts as well. Now, that was in 1975. The next next drastic development that came in this field was with Rodwell-Hoskins in 1996. So this is a dynamical, okay, it works. So what Rodwell-Hoskins said was that monsoons are creating subsidence to their west side, onto their west side. So if you consider the South Asian monsoon, because of latent heat release, the entire troposphere is experiencing diabatic heating. Now, this diabatic heating produces a subsidence to its west. And this subsidence, this is what allows for subsidence to persist over Sahara during the summer season when monsoon is strong. So these are some, this was shown with simple linearized dynamical models. Now, this is one important point that we should consider is that this is not a simple Walker-like cell. So updraft over South Asian region and descent over that same cell descending over Sahara, that is not what happens. Okay, this is not a Walker cell. So what really happens here is, okay, I need to go there. What really happens here is that the diabatic heating over monsoon regions trigger a Rossby wave response, which creates subsidence over deserts. So we have, we can see that over here, you have downdrafts or subsidence over here especially East Asia, and immediately to the west of the monsoon regions. So this subsidence, the air mass that is in this subsidence is coming from mid latitudes and not from the monsoon regions. Right? So this is not a Walker cell, but it's coming from somewhere else. Nevertheless, monsoons induce subsidence to their west side. Okay, so that was the hypothesis, and sorry, it's a stationary response. So this is a very important hypothesis theory that has been able to explain persistence of arid regions, subtropical highs to the west side of monsoons. But there are two important drawbacks in this theory. Firstly, it assumes a diabatic forcing. Where does that diabatic monsoon forcing come from is not addressed. So given monsoon forcing, this is the region where subsidence and arid regions will persist, is the proposition of this theory. Now, going back to the example of the game of chess, in this theory, it is pretended as if the deserts are passively responding to whatever monsoon is doing. So if monsoon plays the queen, deserts will accordingly adapt its strategy. But in reality, monsoons and deserts are having their own strategies. There is a very strong interaction between the two, but that is not considered, or that is not explained in this theory. So subsequently, there were many different studies. For example, these papers here elucidate the different feedbacks from deserts onto monsoons. So it's a two-way feedback. And yesterday also in Gilles' talk, we saw how presence of deserts to the northwest of monsoons limits its northward extent. So these are certain feedbacks that come from deserts onto monsoons. So that is one feedback. Other feedbacks, for example, from dust, explained by Vinod et al. Vegetation and dust over Sahara, Middle East, can influence monsoon. So that's another proposition. So likewise, some other dynamical mechanisms also exist, especially during onset. So what happens is, there is this hypothesis that dry air intrusion from northwest India, the amount of dry air intrusion is a key variable in determining the onset date and also the pace with which onset progresses. So these are certain considerations, certain feedbacks that exist from that come from deserts, but are not considered in Rodwell-Hoskins mechanism. So at this point, I will switch to a simple thought experiment. Now, suppose we take the normal climatological scenario where we have diabatic forcing over the South Asian region. Now, as I said earlier, there is no explanation why this diabatic forcing is over here. So let us assume there is some large-scale feature, large-scale forcing, which enables such persistence of diabatic heating in this region. And we have subsidence to its west, creating this gigantic arid region. We already have now, in a steady state scenario, high albedo over these regions, right? Now, if we reverse Earth's rotation, those same large-scale parameters which created monsoon here, those geographical parameters, the Himalaya, it could be the ocean to the south of the Indian subcontinent, whatever. These large-scale parameters would not have changed much. We still have high albedo, low albedo over India. So it was my expectation that monsoon would still be strong in this region. Now, because the Earth is rotating in the opposite direction, Rossby wave induced by this diabatic heating would be to its east, right? So this is where I was expecting a strong desert to develop. Now, because there is no subsidence on this side, there is no suppression of convection on this side, there could be potential for some small convection occurring, given the condition that there is high albedo already existing. To what extent this uh, induced convection now would grow was the question I had. So basically, I was assuming that there will probably be some increase in rainfall, but not a drastic change. But that is not what our Earth system model told. So basically, going with the predictions of Rodwell-Hoskins mechanism, uh, there is no major difference in the total diabatic heating coming from South Asia. We can see subsidence on the east side now, aligning very well with the Rodwell-Hoskins predictions. But how do we explain this drastic increase in rainfall over Sahara? It has very high albedo, right? We have only changed the rotation of the Earth. We have not changed any, we have not touched the albedo yet. So this is what I was interested in. And therefore, I started examining the transients of this simulation. So we have a climatology, control climatology. And then on January 1st of the model year, the rotation is reversed. So if we trace the transients, can we see how monsoon develops over a very high albedo region? So that was the thought behind examining the transients. So a quick look at how albedo evolved in this simulation. Star here represents the albedo in climatology of the control over Sahara. Now in year one, so x-axis is model year. So I'm showing only the first 300 years. The model was run for 8,000 years. So this goes on for a very long time. So this is surface albedo over the region of interest, Sahara and some parts of Middle East. Year one, albedo is almost same as control. Now you can see that it is exponentially decaying very slowly, and it reaches steady state over a very long period, multiple centuries. So this is due to the gradual growth of vegetation over this region. So if albedo is the limiting factor of precipitation or monsoon, then precipitation should also follow a similar exponential graph, but growing graph, right? This is decaying, albedo is decreasing, monsoon should increase or rainfall should increase. But here is what happens quite interestingly. That's albedo, this is precipitation. Control, it is 0 because it's a desert in control, no rainfall. The very first year, rainfall jumps up quite high in spite of very high albedo, right? And then it gradually increases. So within about 100 years, it is already very close to the steady state value. So this value here is nearly 70% of the steady state value. So this is the fast response and a very slow response. The slow response probably is associated with vegetation feedbacks. This fast response is what I'm interested in. What is it that triggers such a development of monsoon the very first year? So we have only one realization. Now, here is precipitation now in the bottom part of the figure. In the top plot is F2R, the net radiative fluxes over this region. In control, it is slightly negative, right? So kind of goes with the hypothesis that negative F2 subsidence, no rainfall. And in the very first year, it jumps and reaches, it also reaches quite close to the steady state value. And there is a gradual increase over time subsequently. Another interesting thing is that if instead of looking, so this is all JJ, I have taken June, July, August average parameters for the first 300 years. If we look at the daily evolution in the first year, so this is the day when rotation was reversed, and that's 365 days. So first year, the left side is F2R, middle is absorbed shortwave. This is S minus alpha S, absorbed shortwave, and this is OLR. Okay, so let's look at F2R first. The thick line, that is control. Dashed line is reverse rotating world. Both start off, F2R, both start off nearly similar. And after some time, F2R in control saturates, does not increase beyond a certain point. But in control, in reverse rotating world, it goes on further and further, reaches a maximum value, and then goes down following the seasonal cycle. Now, if we look at its components, the absorbed shortwave and OLR, there is no major difference between the two, control or retrograde, in the absorbed shortwave. So, suggesting that the total amount of shortwave energy absorbed by both the simulations or both these scenarios is exactly the same. But what is different is the OLR. And why does OLR increase? It comes, if we look at how this thing evolves, so we can diagnose the changes in P minus E over this region. So we have now, what we have done is, the GMS here takes into account the horizontal advection. So therefore, we can use that equation, which I had introduced earlier, and probably have come across it a couple of times already in this workshop. So this is the difference between, difference in P minus E between retrograde and the control simulation. But this is for the first year, June, July, August of the first year over this region. So there is nearly 3 mm per day increase in P minus E. Major fraction of it is explained by changes in the radiative fluxes at the top of atmosphere. So breaking down the F2R into OLR, shortwave, and surface fluxes, we can ignore surface fluxes here. I'm considering only land, so we can ignore surface fluxes. Most of the changes in top of atmosphere radiative fluxes come from OLR. We can further divide OLR into clear sky and cloudy sky components. I've done some additional things here, but essentially all these three parts put together is the cloud radiative feedback on OLR. And this is just the clear sky OLR. We have nearly, if we add all of these three, they are pretty close, clear sky and cloudy sky. So OLR changed in the very first year over this region, coming from clear sky and cloudy sky, nearly equal parts. So why did OLR change so quickly during the first year? So this has got to do with water vapor. Clear sky OLR depends on water vapor and surface temperature. Now, what happens here is that in the reverse rotating world, we have the low-level jet coming from Bay of Bengal across the Indian subcontinent into Arabian Sea. The arrows here are vertically integrated moisture fluxes, and color is column integrated water vapor. Right? So there is a lot of moisture getting advected over Sahara from Arabian Sea and also some from the Atlantic Ocean. So there is a strong convergence of moisture in this region. And this happens in the very first year. So there is the moment you reverse rotation, some large scale dynamics change, which enables moisture propagation over this region. And if enough moisture gets propagated, then it has an impact on OLR, F2R changes, and then you can have increase in rainfall. So this is the basic working hypothesis from this thought experiment of reversing the Earth's rotation. So what are the implications for modern climate? Here is a plot of F2R for South Asia and Sahara from era 5. Okay, so over Sahara, so during the non-monsoon months, F2I is negative in both South Asia and Sahara. So these are the times when there is no convection in South Asia, and F2I is also negative. Over Sahara, it only slightly becomes positive. Over this box which I have taken, it is slightly positive. In regions, it was negative. We saw this in an earlier plot. But there is a big increase in F2R over South Asia. This is absorbed shortwave, and this is OLR. Now, because South Asia and Sahara are at similar latitudes, they receive similar solar radiation, and there is no major contribution of albedo between the two regions. There is some difference here. If you look at South Asia, during monsoon months, absorbed shortwave is lesser than Sahara. It means South Asia is reflecting more shortwave than Sahara does. Why? Probably because cloud albedo is higher than the albedo of bright sand. So, but this is not the major distinction. The major difference comes from OLR. OLR starts to diverge in these two regions well before monsoon. In the months of April, May, March, April, May itself, they are digressing, right? And during the monsoon seasons, it's a very, very big difference. So what drives these changes? If we diagnose this, it once again comes to nearly equal contributions from water vapor and clouds. Water vapor in the clear sky, clouds in the all sky, so cloudy sky part, right? So now this is a graph which I had shown earlier, but now we are going to revisit this from observations perspective. Y-axis is clear sky OLR. X-axis on the plot to the right is surface temperature. Plot to the left, it is column integrated water vapor. Plus is Sahara. Filled circle is South Asia. Okay, let us look at this first. OLR clear sky, outgoing long wave radiation versus surface temperature, Sahara. So it is an almost linear fit. So outgoing long wave radiation in this region is a simple linear function of surface temperature. But if you look at South Asia, it is linear during the non-monsoon months. The different months have been colored here in different colors. So it is linear almost up till about April, May, with a slightly different changing slope here, and then it is no more linear. So that is from June, July, August, September, and then from October onwards, it slowly starts to be linear. So during the non-monsoon months when enough moisture is not present over South Asia, OLR clear sky is a linear function of surface temperature. When there is enough moisture, something happens. So let us look at the impact of water vapor on OLR clear sky. Now, there is no clean relationship here for Sahara. Water vapor never exceeds 20-25 kilograms per meter square. So over South Asia, the moment it crosses about 25-30 kgs per meter square, there is a negative relationship between the two. So this is mainly in the monsoon months, June, July, August, September. There is some hysteresis type thing here, but largely it is linear, negatively related. So there is something that happens here beyond this threshold. So this is the transition of Euler clear sky from dependence on surface temperature to being dependent on column integrated water vapor. So one more interesting thing that we can do here is diagnose how total OLR. Now we saw how OLR depends on clear sky depends on surface temperature in which months, and in which months it depends on water vapor. Now we can go back to this figure and diagnose the contributions of different parameters. We saw surface temperature, water vapor, clouds. We will add clouds to the difference between these two graphs. So OLR from South Asia, OLR from Sahara, if we take the difference, which parameter contributes the most to this difference is what we will look at. So to do this, I have used RRTMG and prescribed profiles from ERA5. What you are seeing is the difference in South Asia and Sahara of OLR. Now, in black is the total OLR, right? So everything here has been aligned to the onset date. So the 0 is the date of onset. This is pre-onset, 3 months before onset, and this is further into the season. Now, this has been broken down into 3 components: effect of water vapor, clouds, and temperature, surface temperature. This actually includes temperature from surface and atmosphere put together. So if we look at the temperature effect, its contribution is negligible. Blue is water vapor. Water vapor contribution is higher pre-onset, and post-onset, there is a sudden drastic contribution, increase in contribution from clouds. So around the time of onset, how OLR, which parameter determines OLR is different, and that is a very important thing here. So how does this all come together? This essentially tells us that there is radiative heating of atmosphere, mainly in the boundary layer, occurring because of buildup of moisture pre-onset. So just before onset, there is large-scale changes in large-scale circulation, which advencts moisture. Moisture is building up over the South Asian region, which has a direct impact on clear sky OLR. Radiative heating of the atmosphere is also occurring. Subsequently, convection is triggered. You have clouds, and clouds will have an impact on OLR. Right? So so essentially, now putting all of this together, we have a simple hypothesis using the same equation that we saw earlier. This is low-level mass convergence. F2I has been split now: insolation, reflected shortwave, OLR, and GMS. Around the time of onset, some large-scale forcing initially triggers mass convergence in the lower troposphere in South Asian region. This will advect, advect moisture into this region, which has an impact on OLR initially. The moment OLR, so what is the effect on OLR? OLR reduces. So if OLR reduces, F2A, which is the sum of these 3, will increase. Numerator is increasing, then that leads to further increase in convergence, large-scale convergence. This will then increase the moisture advection in this region, which will have an impact on OLR, which will then increase the large-scale convergence into this region. So at some point, convection is triggered, clouds will form. Clouds have an impact on OLR, and also albedo, right? So the moment clouds form, clouds are influencing both OLR and albedo. So then F2I it changes even further, and uh, you have this monsoon onset occurring. Now, this is a very simplified explanation. There are two major omissions that I have made. So, firstly, uh, going back to that point where convection is triggered. For convection to get triggered, we need to have GMS changing. GMS represents stability of the atmosphere. So now when you have enough moisture accumulating, it is it has an impact on OLR and F2R, but it also is reducing GMS. I have not addressed that in while explaining this mechanism. So that is the first omission I made. Now it has been shown already that during onset, GMS has a very important role to play, and quite rightly so. The moment GMS changes, you have clouds forming, and that will further influence albedo and OLR. The second omission I made, or second simplification that I made here, is the assumption that the rate of change of column integrated moist static energy is not going to play a major role. But that assumption is wrong. So I did that, I made that omission deliberately to explain the presence of this type of feedback as well. Now, during the transients, when you are especially looking at onset or around the time of onset, it's a three-way balance. The radiative heating, convergence of importer-export of moist static energy, and the rate of change of column integrated MSC. So it's a three-way balance between these three parameters. So far, for me, it is not yet an answered question, which of these three is the most dominant one. My only proposition here is that there is this loop as well. So that is the only proposition. So the key takeaways from this whole exercise is that the main parameter limiting monsoon or determining the region where you have uh, monsoon and desert is F2R. And I would not think of albedo as the main limiting parameter. If F2I is positive, it's a region of convection. If F2I is negative, it is usually associated with subsidence. Now, having said that, I want to also emphasize that albedo is just one of the two knobs. There is albedo and there is OLR. You can use both of these knobs to change F2R and then impact the region, impact whether it becomes a region of convection or subsidence. So this is the first takeaway for me, that albedo in previous theories, previous propositions, albedo was given quite a lot of importance. I want to suggest that albedo is important, but also we have to take OLR into consideration. If I change, along with changes in albedo, if I also change something else in the system so that OLR changes, then the effects can be compensated or negated. So for me, that is the first takeaway. Secondly, Rodwell-Hoskins mechanism, we have seen that it works in the reverse rotating world, so it is valid and holds well. If there were any doubts, then at least with this simulation, I can say that it works well. So yeah, I think that is all from my side. I'm ready to take questions.
Hello. I really enjoyed your talk. It seems very
Thank you.
interesting. So I have just one query. So when you compared deserts and monsoons, did you simply just consider the hot deserts? Did you account in any way for the cold deserts as well?
No, this is simply Sahara and South Asia.
Just Sahara and South Asia, not
Yeah.
the other monsoon
No, 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 no.
regimes. Okay.
Yes. Yeah, so hi. So in a plot you had showed for the reverse rotation, there is moisture transport, some Somali jet kind of thing from Sumatra.
It works from here.
Yeah, here. So is this the very first year of the simulation or?
Uh, so this is what I have shown here is a steady state, but even in the first year, we have during JJS we have this thing developing.
Okay, so the shading is the column integrated
Yeah.
water vapor, right? So in your precipitation field, I think, how was it like looking?
Yeah. So let us look at this initially.
Yeah, yeah,
So we have quite a lot of moisture over Arabian Sea, Middle East, and then there is a negative gradient going west. Right?
yeah, yeah.
So if we look at this, so you will see quite a lot of rainfall over Arabian Sea now,
Okay.
right? And also following the gradients in moisture, precipitation is decreasing as you go west.
Okay. So a follow-up is like literatures has shown that the presence of Ethiopian highlands over the East African region is so important for the Somali jets presence. So here as well we have a Sumatran
Yeah,
topography. So do you think that
yeah,
something like
maybe,
that? Hmm?
maybe.
Okay. Thanks.
Hey, nice talk, Chetan. Is there a place for regarding untangling these different effects? Uh, you know, things like cloud locking experiments or other sort of ways where you surgically play with the radiation in some way?
Yeah, I think there are two uh, two of these papers which have two of these studies which have done. So Bine, Mike Bine, they have
Mike
used an
Byrne, yeah.
actisymmetric uh, model and then used radiation locking, and Clark et al., which you all, I think mentioned earlier as well, right? So, but while these experiments confirm the radiative impacts of water vapor and very useful experiments, uh, one USP of our study is that we are not tampering with the physics of the model. We are prescribing a boundary condition such that these get untangled organically.
Right, but there's a place still for ancillary simulations that are
Yes, there is. There is.
where you are tweaking the model directly, right? I don't see that at cross purposes with your broader angle.
Yeah, I think I'm just kind of rephrasing what Spencer asked. Can we go to your previous slide uh, where you show water vapor and clear sky OLR?
What?
Yeah. So here, I was just thinking for the same value of water vapor, you could have two OLR, clear sky OLR values, and same for surface temperature, right? So there is some flip,
Yeah, yeah.
right? There's some flip that happens.
Yes.
Probably my hunch is depending upon what altitude you have water vapor at, maybe.
Possibly. That's right. That's possible.
But I think
Like-
maybe it might be possible to chase this if you were to do these kind of spooky, transparent cloud or cloud fix simulations. I think that's what probably Spencer also is mentioning. Although in your mechanism you say clouds are not essential to kind of start the process,
Yes. Not
but you need water vapor
Yeah.
one way or the other brought in by transport.
Yes.
So you think winds should start
Yes. Yes.
from ocean to land
Uh,
and then radiation to have that nonlinear feedback. And if water vapor were to be, sorry, I am not asking question, but making a comment. If somebody else has a question, I'm happy to stop. Yes, yes. So if water vapor were to be transported over warm lands, then I guess Kerry's, I think paper, I don't know, recent paper shows you could build enough cape. And I think there is this progression then.
Yeah. So that's the thermodynamic effect,
Yeah.
which will get triggered subsequently. My proposition is slightly before that, while the moisture is still building up and while cape is still building up. During that time, OLR is reducing. You are heating the troposphere, mainly in the lower boundary layer. This
But
is
the
quite-
winds are still
important.
Are still in the right direction before
Yes,
radiation
yes,
kicks
yes.
in.
So the whole mechanism, the whole thing starts with some large scale
Dynamic kick.
Yes. Now, what it is, I have not addressed. I'm just saying that something will push enough water or begin to push water and then subsequently.
Thanks.
Maybe I'll try to frame it in a. So my question is, because I look at mostly large-scale dynamics, for me, the first thing I would have looked at in this problem would be like the large-scale dynamics. Why didn't you consider that?
So without large-scale dynamics, we do not have the moisture advection over this region. So given that there is some large-scale dynamics which is pushing enough water, what is the subsequent sequence of events that leads to growth of monsoon in a region where I did not expect it to because of high albedo? That was the question I was addressing. So I assume there is some large-scale forcing, large-scale dynamics, which will bring moisture. I started from the other end and stopped at large-scale forcing. I did not probe why large-scale forcing changed. So yeah.
So this is really nice, and I mean this is the framework we've been repeatedly going to, which is the moist static energy budget, and then you do it very nicely here, and you find out everything on the right hand side is a feedback, like nothing actually forces the system in the MSC world.
Not quite.
Well, what's the forcing?
No, everything is not a feedback. Part of the feedback comes from those terms. The moment, let's take the example of the water vapor radiative feedback. Right? So when you have increase in moisture, OLR is decreasing, but at the time, insolation is not, the S is not affected. We are still having radiative heating of the surface because of insolation. So part of the numerator is feedback. So maybe one interesting.
But I still don't understand which is the forcing part. None of the terms that you actually enforce, the solar radiation or anything, change.
What the forcing is the large scale and the
Large scale what?
Yeah, large scale dynamics, large scale circulation.
Yes, you could have dynamics.
Yeah.
Yeah, but that's not in the MSC budget, right?
That is not in the MSc budget. So
Yeah, yes, that's my point. That,
Okay.
this framework which we all use, right?
Yeah,
The
yeah,
field is full of it. it doesn't help you so much here because everything's a feedback. And then in the end you say, oh, well, actually because of geostrophic balance, there's this big moisture transport, and that's the answer. And then, I'm not saying that like the MSc budget's super useful and doing cloud locking and stuff will really
maybe I
tease
did
out
not
these
understand.
things.
I did not understand properly what you were trying to say, but please correct me. So what you are trying to suggest is that the impression here is that on the right-hand side, everything is a feedback.
Yes, that's my impression in this problem. And it's called a forcing, right? We often say it's the net energetic forcing, and it's just manifestly not a forcing here. It's all like the convection is moistening the atmosphere. The convection is, or the circulation is moistening the atmosphere. The OLR is changing because there's now clouds which are associated with the thing you're trying to predict. So it's really, it's sort of almost confuses the.
That's a good thought.
And then in the end you come up with sort of a fairly a different answer, which is that, well, geostrophy tells you the wind goes the other way, so you get some moisture. And
that's
I mean,
thought.
it's just a more general comment. I'm not trying to like say it's your fault. It's just, sometimes I wonder about where we've gone.
Name clash between forcing in the MSc budget sense versus radiative forcing, but in the latter sense, this simulation is unique because there is none, right? You've changed the rotation rate. There's no, unlike almost any other simulation where you're perturbing something. So I wonder if that's relevant, but then there's like I said, there's a danger of. Yeah. So, okay, so then thinking more about my question to you, similar but different, what about just locking the vegetation? Right? Like on the
first year doesn't have a.
That's what I'm saying. But that's what I'm saying is how do we reconcile this with, so from the QTCM work from Neelan and Joe, those papers, right? Like their argument was what keeps the West African monsoon south, as south as it is, the Sahara able to exist is that high surface albedo, and you take that away, and then the so. So in this case, it's just because you now have this massive moisture source from sort of the east. Right. But why not? Why not? Okay. I'm confused.
Is there a critical water vapor beyond which, CWV amount beyond which your radiative feedback sits, and it's the peak of this?
Between 25, somewhere around 25.
And this is verified in a kind of, did you do any, because I know you did single column modeling on this, so just wondering.
I have not verified, but since this is from RF, I assume.
Thanks.
Okay, this is different, but also but still about vegetation dynamics. So at least several years ago, my understanding of the state of modeling of the Green Sahara problem, so totally different problem, right? But the mid-Holocene greening was that the conventional models, even if they had dynamic vegetation, weren't able to self-consistently model that state. You would have to impose a la the QTCM thing I referenced, right? This model, in response to this rotation rate, clearly you have a Green Sahara, right? Do you know, have you guys tried the Holocene forcing and or just more generally in the community at this point? Is that problem is there progress there?
I have looked at this very long back. So what happens is with the green Sahara, mid-Holocene, early Holocene scenario, the orbital configuration is different. So let us keep the vegetation for a little bit later. So just on account of changes in orbital configuration, S minus alpha S is different compared to pre-industrial. Yeah. And this is enough to make F2 a positive over quite large regions of Sahara. And that sort of already explains the increase in rainfall. Now, if you prescribe vegetation, you are changing albedo even further. So that changes S minus alpha S even more, and F2 is different. So that is that can be explained in this way.
What I'm trying to say is models,
Models
even
don't
if
get
they
it.
had if you leave the surface albedo as it is, if you have a static vegetation and you don't change the surface albedo, even if you give it the mid-Holocene forcing, you get a somewhat northward movement, but it mostly stays within the Sahel. Even then, in models that do have dynamic vegetation, wherein in principle the albedo feedback could come in and give you that complete migration, X years ago, none of the models could do that. In your model, in response to something else, this rotation rate switch, you have, in this case, the precip is obviously leading as it sort of needs to for the feedback, right? But you very clearly, over 3 centuries or whatever, get this. And so I'm wondering, does this specific model also, in a Holocene force simulation, self-consistently get that same greening?
It has the same problem. Not enough vegetation, not enough northward propagation. But better than, so for example, we have the trace 21K. It is better than that, but not as much as observation would suggest. Yes.
So can I give you a very dumb theory to refute? What if it's just, the Rodwell-Hodgkin's mechanism tells you have heating and then you have substance to the west. Yeah. So the monsoon kind of goes to the east of the continent, of the big Eurasian, Euro-African continent. And then when you switch the rotation, the substance goes to the east. So it sort of goes as far west as it can. So there's nothing pushing substance on it.
I agree. And for me, the only exciting thing was that I would have jumped to this conclusion if Sahara was already having lower albedo than it did. So the only thing that got me hooked here was that Sahara had high albedo to begin with. So that is why I,
okay, so it overcomes the albedo.
Yes.
But I guess, can you formalize that in some, like you could take like you could put the convection everywhere you can and see whether there's some sort of like negative forcing from the other convection or something. I don't know whether you could quantify that somehow. Anyway, sorry, I should shut up now.
Worth trying. Seeing to what extent albedo will limit, or under what conditions albedo limits, if there is a condition. It would be good.
From this state, start from this state and
reverse again.
And see.
There is one more thing that does happen. Let's see. So what you said does happen in East Asia, right? So to begin with, East Asia is vegetated. So after reversing, you have subsidence. So it should become dry, but something else happens over there. So we have mid-latitude storm interaction because of the orography. We have precipitation during winter, which continues to sustain rainfall. But so that is one complication we get over there. Otherwise, it would have been a very clean case to understand what happens.
One last question. Yeah, yes. You had, I think it was Surat's paper where you showed a stationary Raspberry wave response. So I was wondering if how that westward propagation persists in a background of like westerlies at that latitude? I think it was Surat's paper, I guess.
Yeah, but I did not follow your question though.
No, there was a response Rossby wave here. So I think that latitude usually we have subtropical westerlies.
Yeah.
So how does westward propagating Raspberry wave response like act in a? It's not a very like a resting background, right? It's already filled with background westerlies there.
So this is the steady state solution. So
Okay.
there may be transients,
Okay.
but this is the stationary wave that you get eventually.
Okay. I was wondering just how in the westerly that this kind of a propagation was possible from the east to the west.
Okay, let's thank Chetan one more time and then
Thank you.
yeah, let's break for coffee.